Welcome everybody to Algebra 2, Section 4.6, Dividing Complex Numbers and Classifying Properties of Complex Numbers. Classifying and Properties of Complex Numbers. So we have some scenarios where we're going to be dividing complex numbers, and in all times when we have complex numbers or just any imaginary numbers, we need to make sure that I, the imaginary unit, the square root of -1, cannot be in the denominator by the time we're done. So we have to make sure we remove from the denominator or modify our expression so that I is no longer in the denominator. And how we do that is we multiply both the numerator and denominator by I a lot of times. So if the denominator is what we call a monomial, just one term, there's no addition or subtraction, then we're going to multiply both the top and bottom by I. And so multiply the top and bottom by I and I. What this is anything divided by itself is secretly 1. So even I divided by I is 1. And so we're really only multiplying by 1. And as we multiply this, we get 10i on top. And on the bottom, we get 2i squared. Recall that 2i squared is really just -2 because I squared is -1. And so we get 10i over -2. And I can simplify the 10 and -2, even though one has an I with it. That's perfectly fine since they're multiplying. The 10 and the I are. And so 10 divided by -2 is -5. And so I get -5i as my answer. Now, another perfectly acceptable way to solve this or simplify this problem is to start off with reducing. So you could initially reduce and call this 5 over I, and then multiply the top by I and the bottom by I, and get 5i over I squared, which we know is 5i over -1, which is again -5i. Number 2, 4 over -9i. I'm going to multiply once again the top and the bottom by I because there's an I in the denominator. And I get 4i over -9i squared. -9i squared is just really +9. And so I get 4i over 9. And I'm perfectly content with this. Can't reduce any further. And our I is no longer in our denominator. We're fine with it in our numerator. Number 3 here. -7 over 5i. -7 and 5 don't reduce, but we do need to multiply by I on the top and bottom since there's an I on the bottom right now. And this will accomplish us getting -7i over 5i squared, remembering that 5i squared is really -5. And so we get -7i over -5, which is really +7i over +5, because a negative divided by a negative is a positive. Moving on to number 4 here. Our denominator is still a monomial, even though our numerator is now no longer a monomial. And so what we're going to have to do is we're going to have to multiply the top and bottom by I still. And as we multiply the top and bottom by I, we end up getting 28i minus 8i squared. We distribute the I over 4i squared. Now 28i is just going to say 28i, but remember that -8i squared is really just +8. So we have +8 plus 28i, liking to write the +8 first. And this becomes -4 on the bottom. Now we can reduce this, but we can't just start slashing here. What we instead have to remember is that each of these are individually being divided by -4. And so a good way to try to remember this could be to separate them out into 2 separate fractions. That can be really helpful for a lot of us just to organizationally see the difference here. And so this can help us see that 8 divided by -4 is -2, and 28i divided by 4 is 7i. And we get -2 plus 7i. Now, there is another way to do this problem, and that would be simplifying early. Just like I was talking about with number 1, we could simplify early. And once again, we'd want to make sure that we kind of handle as 2 separate fractions. So 28 over 4i minus 8i over 4i. And the 28 and 4 reduce by 4 to become 7 and 1. And so that's like 7, but that is 7 over I. And the 8i and 4i reduce, the 8 and 4 reduce to 2 and 1. And the I and I just reduce to 1 because anything divided by itself other than 0 is 1. And that includes I as well. And so this ends up just being -2. And now we notice, hey, actually, I don't have to reduce that one at all. That's kind of handy. And as we choose to not reduce that one, we'll just multiply the first one by I over I. Or I don't have to reduce, but I don't have to multiply by I on the second one because there's no imaginary number in the bottom, only on the first one. And so then this will result in 7I over I squared minus 2. And we'd actually want to write the negative 2 first. So I'm going to go ahead and change this. So the negative 2 comes first. The non-imaginary part, the real part comes first. And then we say, okay, well, negative 7 or negative 2 plus 7I over negative 1, which is I squared, which is really negative 2 minus 7I. Oop, I must have made an error here. What did I do wrong that I did not catch? Trying to find it now. Oh, I see what I did. This up here, when I split it, should have been a negative 4. So I need to correct that to make this a negative 4 because it should have been a negative 4 on each of them. Which means that down here in my answer on the first one, oops, that's too big of an eraser. That's better. Down here in my answer, the first one, this should have been a minus 7I. Now the two answers match. So I apologize for that error there with a negative 4 and for getting that for that second fraction with a negative on the original solving of the problem. But you can solve the problem either way, whether you reduce early or reduce later, it's perfectly fine. Number 5, 1 plus 4I over 2I. So once again, you can choose to reduce these early, or you can reduce them late. Here I'll just reduce them late this time, or later. And so this time I only multiply by the I again. I don't multiply by the 2 or anything like that. I distribute the I, and I get I plus 4I squared over 2I squared. And I plus 4I squared is really just negative 4 plus I, because the 4I squared is negative 4. And we like to write that part first. And then this one is negative 2 on the bottom. Now, negative 2 and I can't reduce, but we still can reduce negative 2 and 4. And so I still want us to do that, and that's proper to actually still reduce as much as you can. And so negative 4 divided by negative 2 plus I divided by negative 2. And this gets us 2 minus I over 2. And we just leave that second one as a fraction and call it good, and the first one's no longer a fraction. So we simplified all that we possibly could. On number 6, once again, you could choose to reduce early by 2, if you were to split up the fractions and remember that each one's individually divided by 6I. Or we can just go ahead and off the bat multiply the top and bottom by I, distributing the I, and getting negative 8I minus 2I squared over 6I squared. So this ends up becoming positive 2, which I still don't have to put the plus sign there since the 2 is leading the way, since it's the real part, minus 8I over negative 6. I will now want to divide or simplify each of these. And it can be, once again, easier for us to think through the simplifying process if we make them two separate fractions, which you don't have to. And so this first fraction becomes negative 1/3. Where the negative is does not matter, so I could have it on the bottom like I did in the orange, I could have the top like I do here, or I could have it out in front. And here, negative and negative become a positive, so it's plus, and 8 and 6 reduced by 2 to become 4 and 3, and we still have the I. So it's negative 1/3 plus 4I over 3, and you could leave this as two separate fractions, or personally I prefer to call this negative 1 plus 4I over 3. Now, case 2, sometimes the denominator won't be a monomial. It'll be a binomial, so like it is here, 5 minus I. And if we try to multiply I, ignoring what it says there for a moment for the directions, if we try to multiply by I on the top and bottom, what would happen here is not what we want, so don't write this down. We get negative 2I over 5I minus I squared. And so we have negative 2I over 1 plus 5I as I turn this into 1, and then I write it first. And this didn't actually really help. We still have an imaginary number in the denominator, and if we keep multiplying by I, we're just going to keep getting an imaginary number in the denominator. So since this method no longer works, we need a new method. And that new method is actually something we learned last lesson, where we multiply by the complex conjugate. And if we multiply by the conjugate of the denominator, or the complex conjugate, this will no longer make it so there's no longer an imaginary number in the bottom. The complex conjugate, remember, is a plus bi versus a minus bi. So if this one's a negative, this one will be a positive I. The 5 stays the same. The 5 doesn't change signs, but the imaginary part changes signs. Everything else is the same though. So multiply the top and bottom by 5 plus I. And as we do this, we do negative 2 times both of these, and we get negative 10 minus 2i. And on the bottom, as we distribute this, as we FOIL, quote unquote, we do 5 times 5 is 25. 5 times I is 5i. Negative I times 5 is negative 5i. And negative I times I is negative I squared. And just like we saw last lesson when we multiplied by the complex conjugate, on the bottom, we get the 5i and negative 5i to zero out, and negative I squared becomes positive 1. And now we can call this negative 10 minus 2i over 26. And now we need to reduce. So there becomes quite a few steps to the problems like this. And I'm going to make this 2 separate fractions here to help myself reduce. Eager for you to make it 1 fraction still. That's what I do personally, but I'm showcasing it this way because I have a feeling more of us will succeed if we do it this way. And if we reduce by 2 on the first fraction and actually the second fraction, we get negative 5 over 13 minus I, or 1i, over 13. And once again, you could technically write your answer this way, but I like to make it 1 fraction when they have the same denominator. Number 8. So here, once again, the denominator is a binomial, so we'll multiply by the complex conjugate. Here, the complex conjugate is 6 minus 2i. Once again, the only thing that changes is the sign of the imaginary part. We'll multiply the top by the exact same thing, 6 minus 2i. On the top, as we do this, we end up getting 30i minus 10i squared. On the bottom, as we do this, we end up getting 36 minus 12i plus 12i minus 4i squared. So on the top, this is positive 10 plus 30i, as negative 10i squared is really positive 10. On the bottom, the negative 12i, positive 12i zero out, and the negative 4i squared is really plus 4. So as we combine those on the bottom, we end up having 10 plus 30i over 40. So we reduce this. And once again, a lot of us may have an easier time, or not easier time, but a better time getting these correct, or more likely to be getting them correct if we split this up. We'll put the I on the 30i. And 10 divided by 40 is 1/4, and 30 divided by 40 is 3/4, with the I still. And I'm going to choose to write this as 1 fraction again, since they are the same denominator for each fraction. Moving on, number 9. Multiply the denominator here by the complex conjugate again, because there's a binomial down there. It'd be 4 plus 3i. So that would end up being on the top, 12i plus 9i squared. On the bottom, 16 plus 12i. On the bottom, negative 3i times 4 is negative 12i, and negative 3 times 3i is negative 9i squared. So on the top, this is really negative 9 plus 12i. On the bottom, it's really 16 plus 9. Over here, I'm going to then add those on the bottom and get 25. This does not reduce. 9 does not reduce with 25. 12 does not reduce with 25. So we're done. If you wanted to split each fraction and then try to individually reduce, you could, but we notice once again that nothing reduces here. Number 2. Our complex conjugate this time is going to be negative 3 plus 5i. The 3 is still negative. That doesn't change. The only thing that does change is the sign of the imaginary part. And as we multiply this through, on the top we end up having negative 6 plus 10i. On the bottom we end up getting negative 9, minus 15i plus 15i minus 25i squared. That now, I need to extend this fraction, is on the top still just negative 6 plus 10i. And on the bottom, negative 9 plus 25. So the top is still negative 6 plus 10i, and the bottom is 16. We can reduce, so we will reduce. Once again, a lot of us might have more success doing it like this, splitting up into two separate fractions, rather than handling the reducing in the previous step. Noting that all of these, or both fractions, reduce by 2 though, and we get negative 3 over 5, or 8, plus 5i over 8. And once again, you could write your answer like that, or I prefer when they have the same denominator to write it as one fraction. Moving on to number 11. Here we'll multiply by negative 4 minus 8i, the complex conjugate. The top yields negative 28i plus 56i squared. The bottom yields 16 plus 32i minus 32i plus, minus 64i squared. So on the top, this is really negative 56 minus 28i. And on the bottom, it's really 16 plus 64. So once again, the top is negative 56 minus 28i. On the bottom, we have 80. So once again, I like to reduce these, or we do reduce them, I should say, and I do suggest that you do them individually for many of us. If you don't have to do them individually for you personally, great, good for you. On this type of problem, we would actually need to individualize them though. However, because as we reduce, we notice the first one can reduce by, I'm blanking here. Did I write negative 26? That's a negative 56. Silly Mr. Kossel. I need to fix that here. This should be a 56 on the blue, light blue and the red there. I didn't like my erasing of that one there. So in this first one, the top and the bottom reduce by 8 and become negative 7 over 10. On the bottom one, the top and the bottom only reduce by 4 and become 7i over 20. And so these have to stay as separate fractions because they do not have the same denominator. Moving to number 12. On number 12, we'll notice the numerator is also a binomial. How fun, we get to FOIL twice on the top and the bottom. What we multiply isn't really changing though. It's still the complex conjugate, which is 2 minus I in this case. And so on the top, we have to FOIL here and do 7 times 2, 7 times negative I, 3i times 2, and 3i times negative 3i. Or negative 3i times negative I, rather. And so as we do this, we end up getting 14. I didn't really care for my 14 there. Minus 7i plus 6i minus 3i squared. On the bottom, we end up getting 4 minus 2i. Let me fix mine to minus 2i. Plus 2i minus I squared. The top ends up giving me 14 minus I plus 3. And the bottom ends up giving me 4 plus 1. Notice the top, we're still going to have an I, and that's okay. It's not, we didn't multiply the top by its complex conjugate. You multiply the top by the bottom's complex conjugate. And so the top ends up giving us 17 minus I, and the bottom is 5. 17 and 5 don't reduce, and neither do 1i and 5. Number 13. Once again, multiply by the complex conjugate of the denominator, which would be 2 plus 4i. This ends up giving me 2 plus 4i plus 16i plus 32i squared over 4 plus 8i minus 8i minus 16i squared. And so on the top, we end up getting 2 plus 20i minus 32. And on the bottom, we end up getting 4 plus 16. So the top here is really negative 30 plus 20i, and the bottom is 20. This can in fact reduce, so we will reduce. So negative 30 plus 20i, my apologies, I wrote just plus 20 there. So we're going to write negative 30 over 20 plus 20i over 20. Well, negative 30 and 20 reduced by 10, and we get negative 3 over 2. The other is reduced by 20, and we get I, or I over 1. Number 14, once again, multiplying by the complex conjugate of the denominator. Here would be negative 9 minus I. On the top, we end up getting 27 plus 3i minus 63 minus 7i squared. On the bottom, we get 81 plus 9i minus 9i minus I squared. The top becomes 27 minus 60i plus 7, and the bottom becomes 81 plus 1. So the top here is really 34 minus 60i, and the bottom is really 82. These will reduce, so we do just that. 34 divided by 82 minus 60i divided by 82. The first one here reduces by 2 and becomes 17 over 41. The second one reduces by 2 as well and becomes 30i over 41. And once again, you could technically leave your answer like this. I personally prefer to combine this back into one fraction, however, since they have the same denominator. So that's what I do. Moving on to number 15. Multiplying the top and the bottom by the complex conjugate of the bottom one again would be 5 minus 5i. This results in a numerator of 45 minus 45i plus 30i minus 30i squared. And a numerator on the bottom of 25 minus 25i plus 25i minus 25i squared. Lots of 25s. The top becomes 45 minus 15i plus 30. The bottom becomes 25 plus 25. So we now need to simplify the top and bottom further, and we end up getting 75 minus 15i over 50. These reduce, so I will reduce. And I end up getting, as I split them up, 75 over 50 minus 15i over 50. And the first one's reduced by 25 and become 3 over 2. The second one's reduced only by 5 and become 3i over 10. Next up on number 16, multiplying the top and bottom by the complex conjugate of the denominator, negative 4 plus 3i. On the top, we end up getting 32 minus 24i plus 16i minus 12i squared. On the bottom, we end up getting 16 minus 12i plus 12i minus 9i squared. The top simplifies a little bit more to 32 minus 8i plus 12. And the bottom becomes 16 plus 9. So the top then becomes 44 minus 8i, while the bottom is 25. And 44 and 25 don't reduce, neither do 8i and 25. So this is our answer. Moving on to our next page here, we're going to work on classifying and organizing our number sets. So we have pure imaginary numbers and complex numbers, which are now added to the graphic we had back in Unit 1. Now, a note here, this graphic shows that these numbers that we call the real numbers are actually part of the complex numbers. And we talked about that last lesson a little bit as well. Excuse me, 2 lessons ago, I believe, as well. And the imaginary parts, imaginary numbers, just pure imaginary, where they don't have any addition, subtraction in them, but can have coefficients, are also part of the complex numbers, but not part of the real numbers. And this actually is all the numbers. Once again, as I mentioned the other day, a number that's not a complex number has yet been discovered, and so we assume that they don't exist. Now let's recap a few of these. So natural, remember, are like the counting numbers, aka non-negatives, non-decimals, non-fractions, and not even zeros. So only the positive numbers that are non-decimals, non-fractions. So such as like 1, 2, 3, ... forever, forever. Whole numbers are the natural numbers with 0 as well, so just non-negatives. So 0, 1, 2, ... Integers include negatives, so you got like -2, -1, 0, 1, ... and ... in each direction. But still no decimals, no fractions. Rational, we start introducing some decimals and fractions, so decimals that end, such as 1.2. Decimals that repeat, such as like 0.3 repeating. Fractions, such as 4/3. And once again, all the numbers before it as well. So a number like 2, for example, is also rational. And then irrational, which we said fits in real, but not rational, because it's the opposite of rational, would be a number like pi, which never ends or repeats. And same thing with like square root of 17, for example. Any non-perfect square never ends or repeats. Now the pure imaginary would be like, for example, well, which we use the lowercase I to represent, would be like I or 5i. And the complex numbers then would be like numbers like 5 plus 6i, as well as everything before it. So technically the number 1 is also a complex number. Now, woohoo, we're going to simplify, and then we're going to name all the sets to which a value belongs. So the square root of -64, well, this is really the square root of -1 times the square root of 64. And the square root of 64 is 8, and the square root of -1 is I, so it's really 8i. Now we're all supposed to mention these sets it belongs to. So I will mention that 8i is imaginary, it's pure imaginary I, as well as complex C. So because it has an imaginary number, it can no longer be real, and thus it fits in the pure imaginary as well as complex. Number 2, 10i times -2i. So if we multiply these together, we get -20i squared, which is really 20. 20 is natural, whole, an integer, rational, real, and complex. It is all 6 of those number sets. Number 3, square root of 1 over square root of 9. We do the square root of 1 and the square root of 9, and we get 1 over 3. A fraction. Fractions belong in rational, as well as real, and now complex. You'll notice a theme that all the numbers we'll be covering ever and ever and ever are complex. Number 4, we have some subtraction here between the parentheses. So I'm going to change this to addition and change the signs in the following parentheses to be opposite. Combining my like terms here, 15 minus 9 is 6, and -8i plus 3i is -5i. This has been simplified as far as we can. So we now identify which sets it belongs to, and it's just the complex numbers. No other numbers, because it has an imaginary. It's restricted to only the pure imaginary and complex. And it's not pure imaginary because it has addition subtraction, either one. Number 5 here, 4 minus I times 9 plus 5i. So we first have to FOIL this or multiply through. And we end up getting 36 plus 20i minus 9i minus 5i squared. And as we work to simplify this, we end up getting 36 plus 11i plus 5, which becomes 41 plus 11i. And that's as far as this one simplifies. And as we simplify this far, we can see that it's only a complex number, an imaginary number that has addition and subtraction as well. Number 6, I to the power 41. So remember, we take the power and divide by 4 because the value of I repeats every 4 powers. And once again, as we divide this, we really don't care about the number before the remainder. We only care about the remainder, which is 1. It happens to be 10, remainder 1, but we don't care about the 10. This tells us that it's really I to the first, or just I, which fits in pure imaginary and complex. So that can be confusing that we have I here and I here, because it happens to be what this simplifies to, as well as the number set it belongs to. So be careful there. That's why I'm using different colors to distinguish the two parts of the answer. Number 7 here, negative 2i to the third power times I squared to 7 to the second power. So I'm going to cube this first one. Negative 2i times negative 2i times negative 2i would be negative 8i cubed times the other parenthesis, I squared to 7 times I squared to 7 is really 7i squared. Square root of 7 times square root of 7 is 7, and I times I is I squared. Now I'm going to multiply these together, and I'm going to get negative 56, I to the fifth. Reminder that when we multiply the same bases of I and I, we add the exponents to get 5. Now we divide 5 by 4 and get 1 remainder 1, and that tells us that we would have negative 56i. This fits as a pure imaginary number as well as a complex number. Number 8. As we multiply through, we get 9 plus 15i minus 15i minus 25i squared. This ends up becoming 9 plus 25, which is just 34. 34 is a natural number, a whole number, rational, integer, rational, real, complex. Now, it's not wrong if you were to put rational then integer. It's just typically more straightforward to go from the smallest number set to the biggest number set in order like we did here. Number 9, I to the power of 16. So we take 16 divided by 4. Once again, do not care about anything other than the remainder, really, which is 0. It happens to go into it 4 times before that remainder of 0 happens. And so this is I to the power of 4, which is really just 1. And 1 is a natural number, whole number, integer, rational, real, and complex. Number 10, square root of 150. This is really the square root of 25 times the square root of 6. The square root of 25 is really 5 times the square root of 6. That's as simplified as we can. This is irrational, so the capital I for irrational, lowercase I for imaginary. It is still real, and it is complex. It is irrational because it ends with this non-perfect square root involved. Now, if I had a non-perfect square root, if this was like 5i squared to 6, it would no longer be irrational and real. It would only be complex and pure imaginary. Now let's talk about some properties of complex numbers. So the properties of real numbers, such as the commutative, associative, identity, additive and multiplicative identity, and additive and multiplicative inverse, and distributive, can also be applied to complex numbers. They're true for all numbers in this set as well as the sets before it, such as rational, real, you name it. So we're supposed to write an example of the property using complex numbers. So the commutative property of addition. Remember the commutative property of addition, commutative property in general, says we can do operations in any order we want, such as, or excuse me, do the same operation in any order we want. So we could add in whatever order we want, or we can multiply in any order we want. Here it specifies that it's for addition. So we're going to show a property, we're going to show an example where it adds in any order we want. So for example, we could do 3 plus 4i is the same thing as 4i plus 3. They're equivalent even though we write the 3 first. The associative property of multiplication says that the grouping of multiplication doesn't matter. The way things are grouped doesn't matter when you multiply. The same thing is true for addition. And so an example here could be like 2 times the quantity, I'm going to do brackets to make my life a little bit easier, of 3 times 4 plus 5i. So here 4 plus 5i are in the big grouping symbol and we've multiplied first. That's the same thing as if you were to have 2 times 3 in their own grouping symbol. And then after that, you multiply by 4 plus 5i. You'll get the same result either way. Next, we'll do the distributive property. Distributive property says you can multiply a quantity outside a grouping symbol to the quantities inside a grouping symbol that are adding or subtracting. So for example, 5 times the quantity of 6 plus 7i is equal to 30 plus 35i. The identity property of multiplication states that any number times 1 is itself. It's also known as the multiplicative identity. And so for example, 7i times 1 is 7i. There's also an additive identity. Remember that the additive identity is adding 0 to something does not change the value. And last but not least, the inverse property of addition or additive inverse. There's also a multiplicative inverse. So a lot of times we call it additive inverse and multiplicative inverse. And this saying a number added to its opposite is 0. And its opposite is just the same things, different signs. So for example, if we have 3 minus 8i, and we add that to its additive inverse, the additive inverse would be negative 3 plus 8i. We change the signs of both. So notice it's different than the complex conjugate, where only the sign of the imaginary part was changed. And this would end up equaling 0. The multiplicative inverse is the reciprocal of the original term. And that always gets you back to 1. So now below on questions 16 through 21, we're supposed to say which property justifies the statement. So on number 16, we start with 2i outside of a parenthesis here, and 2i ends up getting multiplied with 7, as well as with negative 5i. This tells us that 2i was distributed, so it's the distributive property. On number 17, we see a number and its reciprocal being multiplied to equal 1. A number multiplied by its reciprocal equaling 1 is an example of the multiplicative inverse, which I will shorten to mult inverse because I'm lazy, but it's the multiplicative inverse. A number times its reciprocal is always 1. On number 18, we have negative 5 plus 4i plus 9i is equal to negative 5 plus 4i plus 9i. So these are still in the same order, negative 5, 4i, 9i, negative 5, 4i, 9i. So it's not the commutative property because they didn't move around, but the parentheses moved. So they're now in a different grouping, and it tells us to do different problems first. So this is a commutative property, which means the associative property. The commutative property is if the numbers themselves would have moved. And specifically, it's the associative property of multiplication, which means addition here because you're adding. But it is still the associative property regardless. And if you just wrote associative property, I'd be okay with that. But once again, it is of addition technically because there are plus signs. On number 19 here, we're saying that negative 12 plus I added to 0 is itself. That's saying a number plus 0 is itself. That's the additive identity. Anytime you end with what you started with, it's an identity. We just have to figure out whether it's multiplicative or additive by whether we're adding 0 or multiplying by 1. Number 20 here, we have negative 6i times 2i times 8i is equal to 8i times negative 6 minus 2 times 2i. So we notice what's in the parentheses did not change, so it can't be associative because we're not grouping them any differently. However, we notice the 8i was second and now it's first, and the parenthesis was first and now it's second. So this means things got moved around to different orders. And so this is the commutative property and specifically it's a commutative property of multiplication since we're multiplying. But if you just call it the commutative property, I'm fine with that. The reason I'm not fine with just calling it inverse and identity, though, is because the multiplicative inverse is different than the additive inverse because one's reciprocal, one's the negative version or opposite sign version. And the additive identity is different than multiplicative identity because additive identity, you add 0. Multiplicative identity, you multiply by 1. Number 21 here, we have 7 minus 2i plus the negative version of 7 minus 2i, aka a number and its opposite sign equals 0. That is, as I just mentioned, or just talked about, the additive inverse. Number 22, we're supposed to name the additive and multiplicative identity of 6i. So what could we add with 6i and keep it the same? And what could we multiply with 6i and keep it the same? Well, the additive and multiplicative identities are always the same no matter what number we're multiplying or adding with. The additive identity is always 0, and the multiplicative identity is always 1. Name the additive and multiplicative inverse of negative 8 minus 3i. So additive inverse means that you change the signs. It's the opposite sign. So additive inverse here would be 8 plus 3i. Whereas the multiplicative inverse would be the reciprocal, or 1 over negative 8 minus 3i. And whether you have the parentheses there is optional. Now we're going to put true or false on these next 5 problems, and if it's false, we'll provide a counterexample. The set of complex numbers is closed under addition. What closed means is that if you perform the operation, in this case addition, between 2 complex numbers, you will 100% of the time get another complex number. And the answer is that true is true. Since every single number ever is a complex number, that means if you add 2 complex numbers, you'll get another complex number. So if you add any 2 numbers, it's still a complex number. And the same thing's true for division, because once again, every number, not just most numbers or we haven't learned them yet, but every number is complex. That means if you divide 2 complex numbers, you also get a complex number. Now, it doesn't mean there's necessarily an imaginary part with them, because remember, like the number 2, for example, is still complex. A good rule of thumb is that really every operation is closed under the complex numbers, or the complex numbers are closed under every operation. All complex numbers are pure imaginary numbers. That is false. There's a whole section in our table earlier where there's complex numbers that are not pure imaginary. And so one example could be like 7 plus 2i. Anytime there's an imaginary where you're adding or subtracting something to it. Number 27, a number cannot be both irrational and complex. Well, that is false. It is perfectly possible for a number to be both irrational and complex. And the first and foremost reason is because irrational is inside complex numbers. It's inside this whole area of complex numbers. So that's the first reason why, is that visually we can see that. The second reason why could be something like this, where you would have square root of negative 47 plus 3. Or really I should do the 3 plus first. And that's the same thing as 3 plus I times the square root of 47. So it's irrational because there's a square root of 7. Or square root of 47 is irrational since it's a non-perfect square. It would never end or repeat. And I is imaginary, so that makes it the complex part. And also, actually, any irrational number is automatically complex anyway. So even if I were to just have, as a counterexample, the square root of 17, that is both irrational and complex. And last but not least here, number 28, the product of a real number and a complex number is another real number. and this is false. For example, if I were to take 2, a real number, times 3 plus 2i, a complex number, I will not be getting a real number. I will be getting 6 plus 4i, another complex number. Now, there are cases where you can multiply a real number and a complex number together and get a real number. But this is a counterexample to that, and that's really anytime you have an imaginary part as part of the complex number. And that wraps up section 4.6 of Algebra 2.